in this question, we're given a chemical equation tells us that ethanol decomposes into ethylene gas and water, and it tells us that ethanol, which is the reactant, when you just take the concentration of that and plot it as a function of time, we just get a straight line. And we're also given the slope of that line, and then we're given a series of questions down here. The first thing to cue in on this problem is that if we're told that we have a plot of the concentration of something with no operation on it, so we're not taking the inverse of it or the natural log of it, and we're plotting as a function of time and it gives us a straight line, then we know that we have a reaction that is 0th order. And so before I even look at the rest of the question, I'm thinking about this. I'm saying, okay, this is a 0th order reaction. Zeroth order reaction. And so that tells us a lot, since this is we're dealing with kinetics here, that tells us a lot about everything else, or we're kind of what we're going to need for this problem. So if we look at the first question here, it says determine the rate law and the integrated rate law and the rate constant. So the rate law, specifically what they're talking about for the rate law is they're talking about the differential rate law, which we just usually call the rate law. And that is always going to be the rate, and we're going to set it equal to the rate constant multiplied times the reactant raised to some power, x. So in this case, we know that it's 0th order. And so we know that x is just equal to 0. But if x is equal to 0, then what that means is that this here, no matter what the number is, right, that's going to become 1. And so we can just get rid of that altogether. And we realize that the rate is just equal to k, which is what we expect for a 0th order reaction. Because in a 0th order reaction, the rate is not dependent at all on the concentration of the reactant. Let's see. And then, so the next question is, or the next part of this question is, what is the integrated rate law? And so for this, we just look at what the integrated rate law is for a 0th order reaction. And it tells us that for a 0th order reaction, the concentration of the reactant at some particular time can be calculated by taking the negative of the rate constant, multiplying it times t, and then adding it to whatever our initial concentration was of that reactant. And then finally, it's asking what the rate constant is. And so for the integrated rate law is written out in the form of a line. It's y equals mx plus b. And we see here that m is negative k. And so for a 0th order reaction, the slope of this line, if we plot concentration versus time, the slope of the line is the negative of the rate constant. So that means that negative k is equal to m. And so we see that m is equal to negative 4 times 10 to the minus 5th per what they tell us in the problem. And that's in inverse liters, inverse seconds. And so if we set this equal to, negative k, then we see that these negative signs just disappear, so we can just get rid of those. Not much of a calculation to do there. But that takes care of part A. So now we know the differential rate law is just the rate is equal to k. So we don't have to keep this in there, it's just rate is equal to k. And then we know that the integrated rate law is this 0th order description of what the rate law should be. And then we also calculated the numerical value for k by recognizing that whatever the slope is of this line, we should just take the negative of that, and that gave us our value of k. In the next part of the question, or in part B of this question, it's asking us to calculate whatever the half-life is. And so the half-life equation, you can either figure out what a half-life equation is by deriving it from this. You can substitute in 1/2 the initial value. So take this and divide it by 2 and substitute it in over here and solve it. But usually it's just easier because you're only dealing with 0th, first, and second order reactions to just memorize them, especially for a test taking situation. Regardless, the equation that you should end up with, memorized or derived, should be equal to this. It tells us that the half-life of the reaction is equal to the initial concentration of whatever ethanol is divided by 2 times the rate constant. And so if we plug in our values, so we're given the initial concentration of ethanol over here, we can plug in our values. And we see that we have 0.05 moles times inverse liters divided by 2 times the rate constant, which we calculated back here. And that's 4 times 10 to the minus 5th mole inverse liters inverse seconds. So put that in our calculator. 0.05 divided by 2 divided by 4. And we end up with 625. And if we come and look at our units over here, we see that moles and moles cancels out, inverse liters and inverse liters cancel out. And so we end up with the 625 over inverse seconds. Of course, we write that as 625 seconds. So the half-life for this reaction is 625 seconds. And that takes care of this part B of this problem. And now we can move on to this last part, which is part C. So in part C, we're being asked how much time for all of the ethanol to decompose. So we can use, whenever you're asked to relate concentration, which is what they're asking for here, how much time for all of the ethanol to decompose, they're asking for how much of this, the concentration. With respect to time, if you're asking to relate those two things, you're almost always using the integrated rate law, or some form of it like the half-life. But you're not using, the main thing is you're not using this differential rate law here. That's not helpful for this. We're going to be using this equation. So if we look at this equation that we already kind of came up with up here, it takes the concentration of ethanol at some particular time and relates it back to the initial concentration over here. So the initial concentration is set. That's what we're given this in the previous problem. So we know that. I'll go ahead and write that down. That's going to be equal to 0.05 moles per liter. What else do we need though? So we've got this. We're looking for time. That's the question, how much time? So T is our unknown. We only have one equation here, so we need to know everything else if we're going to solve for T. What's K going to be equal to? Well, we already figured that out. K is just equal to 4 times 10 to the minus 5th. And then finally, what are we going to plug in for our value of ethanol here? Well, we're looking for the time in which ethanol is equal to 0, when it's fully decomposed. So when does this go to 0 is the question. And then we can just go ahead and plug in and solve our equation. So here, I think it makes sense to always solve for the variable before you start plugging numbers in. So you want to rearrange that equation. And what we should come up with if we do that, let me go ahead and move this over to make a little bit of room. So if we go ahead and do that, let's see, we'll end up with T is equal to the ethanol concentration at some time T minus the initial concentration of ethanol. and all of that is going to be divided by negative k. Here it simplifies rather quickly because remember that this is just 0. And so in order to solve this, we need to take T, plug in what our initial concentration is of ethanol, and divide by K. So there's negative signs out front here, but those negatives cancel out, so we don't have to worry about them. And so what we end up with is 0.05 moles inverse liter seconds. Nope, sorry, just 0.05 moles per liter. Getting ahead of myself, those are the units for the rate constant. Yeah, so in the denominator we plug in our value for K, which remember we just have from up here and we rewrote over here, and that's 4 times 10 to the minus 5th, moles inverse liters inverse seconds. And then if we punch that into our calculator, what we see is that it takes 1,250 seconds for this concentration to go to 0, or about 20 minutes. And that is it. That's how you solve these problems.